physicsinfo.co.uk. Another in the series of Physics GCSE tutorials. Combined Science. Radioactivity, Topic 6. We're going to start this video by looking at the history of the atom. The original name atomos comes from the ancient Greek for uncuttable. And then J.J. Thomson found that there were electrons, so it was even smaller. Rutherford decided that the nucleus was very compact. And then people like Bohr went on to describe electron shells.
But back in the 19th century, scientists thought that everything on Earth was made of just over 80 elements. These elements were famously arranged in a periodic table by Dmitri Mendeleev. At the time, it was thought that elements were made of indivisible spheres called atoms. But each of the elements behaved in a different way. Did that mean that there were 80 different kinds of atom? And if so, what made them different? Were they different shapes or sizes? Or maybe the atoms were divisible. Maybe they were built of even smaller objects.
Everything is made of atoms. But what are atoms made of? Scientists used to believe that atoms were solid particles, like tiny snooker balls. They thought atoms couldn't be split apart. This idea was changed in 1897 by J.J. Thomson. He was investigating the properties of cathode rays using this piece of equipment, an empty glass tube. Here's a modern version of Thomson's apparatus, an evacuated tube containing an anode and a cathode. Heat the cathode and it produces a beam of cathode rays. The beam cuts across a fluorescent screen. Scientists knew that a magnetic field could deflect the path of a cathode ray beam. Turn the magnet round and the beam is deflected in the other direction. Thomson measured the size of this deflection. He worked out that cathode rays were made of tiny particles, hundreds of times smaller than an atom. Thomson was also the first to deflect these beams with an electric field. The screen sits between two horizontal charged plates. An electric field between the plates deflects the path of the beam upwards. The positive plate attracts these cathode rays. The negative plate repels. Reverse the connections so that the polarity swaps over and the beam is deflected in the opposite direction. Again, attracted to the positive and repelled by the negative. From this, Thomson concluded that cathode rays must be made of negatively charged lightweight particles.
Thomson had discovered the first subatomic particle, the electron. Thomson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how did the electrons fit inside the atom? Thomson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body.
This was the so-called Plum Pudding model, where negative electrons are embedded in a mass of positive charge, the radius of each atom being about 10 to the minus 10 meters.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now, if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounce right back.
This is an animation of Rutherford's experiment where he fired alpha particles at gold foil. Now, we would call that gold leaf. Now, Thomson's model was of a positive sphere with electrons embedded, so it was expected that the alpha particles would pass straight through. He described it as firing a cannonball at tissue paper. The results were somewhat different than expected. Most alpha particles did indeed pass straight through. Some were deflected by small angles, but some were deflected by large angles, and even a few bounced all the way back. The cannonball had been sent back by the tissue paper.
After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are.
Using the animation again, Rutherford proposed that because most of the alpha particles pass straight through, that the atom was largely empty space. With very few deflections, the nucleus had to be small and dense. And because some of the alpha particles bounced back, the nucleus had to have a positive charge to reflect the positive alpha particles. We'll look at electrons and electron shells a bit later.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself.
Thomson had discovered the electron, and Rutherford had shown that atoms have a small, dense, positively charged nucleus. Next, they needed to find out what, if anything, made up this nucleus.
Following Thomson and Rutherford, scientists have now discovered lots of particles inside the atom. You need to know about 3: the proton, the neutron, and the electron. A proton has a positive charge. A neutron has no charge. An electron has a negative charge. The nucleus of most atoms is made up of protons and neutrons. The only exception is the hydrogen nucleus. It contains just 1 proton. Each nucleus is tiny compared to the rest of the atom, which is almost all empty space. The only things there are electrons orbiting the nucleus at very high speed.
Just to clear up any confusion between beta minus and positrons, when you get a beta minus, a neutron turns into a proton. When you get a positron, a proton turns into a neutron. In summary, protons have a charge of +1 and a mass of 1 atomic mass unit. Neutrons a charge of 0 and a mass of 1. Electrons a charge of -1 and 1/2000th of an atomic mass unit, and the positron, which is a positive electron, a charge of +1 and a mass of 1/2000 of an atomic mass unit.
The periodic table is the most popular chemical pin-up in the world. In every science lab, you'll find the elements set out in exactly the same order. The layout isn't alphabetical, but it isn't random either. Every element in the periodic table is arranged in order of increasing atomic number. To understand atomic number, you need to look into the heart of an atom. Take hydrogen, the first element in the table. Orbiting around the outside of each hydrogen atom is one electron. And in the nucleus is one proton. Like all protons, it has a positive charge. Every hydrogen atom is the same. The atomic number is simply the number of protons in the nucleus. A hydrogen atom has one proton, so hydrogen's atomic number is 1. Atomic number is usually written to the bottom left of the element symbol. So what about the next element in the table, helium? What's its atomic number? Helium has 2 electrons orbiting around the outside. In the nucleus there are 2 protons and 2 neutrons. The atomic number is simply the number of protons. So the atomic number of helium is 2. The next element along the periodic table is lithium. Orbiting round each lithium atom are 3 electrons. In the nucleus there are 3 protons and 4 neutrons. So what's the atomic number of lithium? The number of protons is 3, which means that the atomic number is also 3. As you move across a row from left to right, the number of protons increases by 1, so the atomic number also increases by 1. An element's atomic number determines its position in the table. Another number you need to understand is called the mass number. The mass number at the top position is usually a bigger number than the atomic number at the bottom. Move along a row, the atomic number increases by a steady unit of 1 each time, but the mass number changes by irregular amounts. To understand mass number, once again, we need to look inside an atom's nucleus. Mass number is the number of protons plus the number of neutrons. Hydrogen has just 1 proton in its nucleus and no neutrons. Its atomic number is 1, and its mass number is also 1. So what about helium? It has 2 protons and 2 neutrons. 2 plus 2 is 4, so the mass number of this helium atom is 4. Next, look inside a lithium nucleus. Can you work out its mass number? 3 protons and 4 neutrons mean the mass number is 7. Each element has a unique atomic number. It's the number of protons in an atom's nucleus. It also tells us the number of electrons orbiting an atom's nucleus.
It was the Danish scientist Niels Bohr who came up with a mathematical model for electrons orbiting the nucleus. He proposed that electrons existed in fixed shells of fixed energy and of limited capacity.
To show how electrons orbit the nucleus, we're using a model. Here, electrons are represented by roller skaters. The orbits occupied by the electrons are circles. The nucleus is the square in the middle. Each atom has the same number of electrons as protons, so if the atomic number is 12, there are 12 protons and 12 electrons. But where are these found? Electrons don't move at random. They circle the nucleus in orbits called shells. Each shell holds a fixed number of electrons. To take a closer look at how these shells are filled, we're going to start with the 3 simplest elements: hydrogen, helium and lithium. Hydrogen has an atomic number of 1. It has 1 proton and so 1 electron. This single electron goes into the first shell nearest to the nucleus. Next, helium. Its atomic number is 2, so it has 2 electrons. They both go into the first shell. But what about lithium, which has 3 electrons? 2 is the maximum number for the first shell, so the third electron has to go into a second shell. There's a limit to how many electrons each shell can hold. The first shell holds a maximum of 2 electrons. The second shell holds a maximum of 8 electrons. The third shell can also take 8 electrons.
This is a representation of the neon gas we were talking about earlier. The model of the atom keeps changing and improving, but we've seen that electrons in an atom exist in shells of fixed energy. So let's explain why neon gas gives off an orange glow when a current is passed through. Electromagnetic radiation, in this case green light, can provide exactly the correct amount of energy for an electron to jump energy bands, energy levels. This electron will stay there for a short while before falling to a lower energy band, in this case emitting orange light. Electrons will absorb light of very specific frequencies, giving an absorption spectra, and then they'll fall down a shell level and give off light of another specific frequency. By definition, all atoms of the same element contain the same number of protons. That's the atomic number. Isotopes of an element have the same number of protons, but the number of neutrons, and hence the mass number, varies. Isotopes of an element are atoms with the same number of protons but different numbers of neutrons. As a result, they have different masses. Thomson and Aston investigated neon and found 2 isotopes, one with 10 protons, 10 electrons and 10 neutrons, the other with 10 protons, 10 electrons and 12 neutrons. These are the 2 isotopes, neon 20 and neon 22. The total number of protons and neutrons gives you the mass number. Actual mass is a little bit different because of the electrons, but they're so small we tend not to count them.
A typical atom, this is an atom of the element carbon, has 3 types of particles: protons, neutrons, and electrons. The protons have a positive charge, the electrons have a negative charge, and the neutrons have no charge. There are the same number of protons as electrons, so the atom overall is uncharged. Atoms of different elements have different atomic numbers. The atomic number is simply the number of protons. For carbon, it's 6. Add together the number of protons and neutrons, and you have the mass number. 6 plus 6 is 12, so this is an atom of carbon 12. What is this? 6 protons, 8 neutrons, 6 plus 8 equals 14. Atoms of the same element with different mass numbers are called isotopes. This is carbon-14.
Moving on to radioactivity, or we should more properly call it ionizing radiation. Unstable nuclei will decay randomly in a number of possible different ways to try and become more stable. They can emit particles from the nucleus, such as alpha or beta particles, or they can give off electromagnetic radiation in the form of gamma rays. When a nucleus is big and it contains lots of protons and neutrons, it tends to be unstable and will kick out particles to find a better stability. Alpha decay is when 2 protons and 2 neutrons leave the nucleus, leaving a remaining smaller atom plus the helium nucleus.
Some elements have many more neutrons than protons. These are the elements with large atomic numbers. For example, uranium-238 has 92 protons and 146 neutrons. The imbalance makes the nucleus unstable. It emits a particle which consists of 2 protons and 2 neutrons. It is actually a nucleus of a helium atom. This type of emission is called alpha radiation. Because the particles are large, they collide frequently with atoms in the paper. They lose their energy and stop quite quickly. As the uranium-238 emits the particle, it becomes a new element, thorium-234, with different mass and atomic numbers. The helium atom completes the equation.
When a radioactive atom emits alpha radiation, it loses an alpha particle from its nucleus. Each alpha particle is made of 2 protons and 2 neutrons. Alpha radiation consists of positively charged particles.
Beta decay, a neutron splits into a proton and an electron, which is ejected from the nucleus. The proton number goes up.
Emissions from elements with much smaller atomic numbers are different. In this process, a neutron changes into a proton and an electron is emitted. This is called beta radiation. The beta particle is very small, so is much less likely to collide with other atoms and can therefore penetrate much further. In beta emission, the mass number stays the same, but the atomic number increases by 1. The carbon-14 has decayed to become nitrogen-14.
When beta radiation is emitted, a neutron in the nucleus splits into a proton and an electron. The electron shoots out of the nucleus at high speed. Beta radiation is a stream of high-energy electrons. This electric arc is also a stream of electrons. See what happens when a magnet is placed nearby. Because electrons are charged, their path can be deflected by a magnetic field. The same would happen with beta radiation.
Comparing the 2 types of emission, the alpha particle is much larger than the beta particle. Alpha is stopped easily, beta travels further.
Finally, gamma decay occurs when the nucleus rearranges. The protons and neutrons find a more stable configuration. The atomic number doesn't change.
Often when an atom loses alpha or beta particles, it's still unstable. It can lose more energy in the form of electromagnetic radiation. This is gamma radiation. Because gamma radiation doesn't involve the emission of a particle, it has much greater penetrating power than either alpha or beta.
Unlike alpha and beta, gamma radiation is an emission of high-energy rays. It isn't made of charged particles, so won't be affected by a magnetic field.
Ionizing radiation can be detected by photographic paper, as with the Rutherford experiment, or the Geiger-Müller tube. Units are counts per second or becquerels. The unit of activity is the becquerel. Geiger counters can be used to show that radiation is everywhere, and this is called background radiation and can come from rocks, space, food, hospitals, even from us.
This sign is known all over the world as the hazard symbol for radioactivity. The radiation emitted from a radioactive source is invisible, but a Geiger-Müller tube attached to a counter can detect its presence. The greater the number of clicks, the higher the level of radiation. Remove the radioactive source and the count falls, but it doesn't drop to zero. Wherever you are, there's always a low level of so-called background radiation. Whether you're out in the street, in the middle of the countryside, even inside your home, a Geiger counter continues to detect low levels of background radiation. That's because all sorts of materials are naturally radioactive. This rock contains the element uranium. Even this wall tile is emitting radiation. And just listen to this old watch. The luminous paint on its hands contains the radioactive element radium. This is the amount of potassium chloride in an average human being. A small percentage is radioactive. Cosmic rays reaching us from outer space also contribute to the general level of background radiation. The cloud chamber also makes the effect of some nuclear radiation visible. The chamber contains air saturated with alcohol vapor. The metal disc in the middle is a radioactive alpha source. As the radiation shoots through the alcohol, it leaves behind a vapor trail. That's because nuclear radiation ionizes air. When the radiation collides with atoms in the air, it dislodges electrons. These air particles become positively charged ions. As the radiation passes through the air in the chamber, it leaves a trail of positive ions behind. The surrounding alcohol molecules condense on these ions to form a trail of tiny droplets. In this way, the path taken by the radiation becomes visible. Although nothing appears to be happening, all these substances are emitting nuclear radiation. It's invisible, but an easy way of detecting it is to use a Geiger-Müller tube attached to a counter.
Now just a brief look at how the Geiger-Müller counter works. Ionizing radiation passes through a mica window, which allows the radiation through but prevents the argon gas at low pressure from escaping. Radiation hits the gas and produces ions, which get attracted to the anode and the cathode, producing a small electrical signal.
There are 3 different types of nuclear radiation: alpha, beta, and gamma.
Let's look at the dangers of the different types of ionizing radiation. The production of ions inside a cell can cause mutations. The best protection is shielding, distance, and time. The alpha particle is a helium nucleus with 2 protons and 2 neutrons. It has a 2+ charge and is highly ionizing. It is not penetrating and will travel only a few centimeters in air. Hence, the risk is low.
This is an alpha source. At this distance, the count rate is about 500 per second. Place a thick sheet of paper in its path and all the alpha radiation is absorbed.
Beta-minus particles are fast-moving electrons with a charge of -1 that are emitted from the unstable nucleus when a neutron turns into a proton. They have a range of energies and can penetrate up to a few centimeters into the body. They are dangerous.
This is a beta source. It emits only beta radiation. The count rate is over 600 per second. Place a piece of paper in its path and the count rate falls only slightly. Some of the beta radiation has stopped, but most travels through. Replace the paper with a denser material and the count rate drops much further. Beta radiation is absorbed by a thin aluminium sheet.
Gamma rays, unlike alpha and beta, are not particles. They are electromagnetic waves. Highly penetrating, they are not very ionizing. In small numbers, their risks are low.
Cesium-137 is a source of gamma radiation. At this distance, the count rate is about 50 per second. Place a piece of paper in its way and nothing happens. A thin sheet of aluminium also has no effect. Gamma radiation is very penetrating. Several pieces of lead are needed to absorb this high-energy radiation.
To summarise, we have large alpha particles with a 2+ charge. We have positive electrons, positrons, and negative electrons, beta-minus, both with a tiny mass. And finally, gamma rays, which are electromagnetic radiation. And finally, radioactivity half-life. Half-life is defined as the time taken for half of the radioactive nuclei in a sample to decay. In other words, it's the time taken for the activity of a sample, measured in becquerel, to fall to half its original value. This time can be measured in seconds, hours, days, or thousands of years.
Some radioactive sources decay very quickly, with a half-life of only microseconds. Others have a very long half-life, running into millions of years.
Radioactive atoms decay, emitting radiation to form new atoms. The sample gradually becomes less radioactive. To investigate decay more closely, this is a sample of barium-137M. At time 0, the activity is 40 counts per second. After 2 minutes, it's dropped to 25. 4 minutes and the count rate is 15. After 6 minutes, it's about 7. The time taken for the activity of the sample to fall by half is known as its half-life. Plotting a graph of count rate against time produces a smooth curve. The activity falls to half its original value in just 2.5 minutes. It falls by half again 2.5 minutes later. So the half-life of barium-137M must be 2.5 minutes.
But each radioisotope has its own rate of decay. For example, iodine-131 has a half-life of only 8 days, while chlorine-36 has a half-life of 300,000 years. Suppose you had 32 grams of sodium-24, which has a half-life of 15 hours and decays into magnesium-24, a stable form of magnesium. An understanding of half-life and some simple math can help you determine how much of the original material exists after a given period of time. After 15 hours, half of the sodium-24 would have decayed into magnesium-24, leaving 16 grams of the original isotope. After 30 hours, there would only be 8 grams of sodium-24 left, and so on, until there's not enough sodium-24 left in the sample to detect its radioactivity.
And that's it. Thank you for watching.